Hello, it's Keith here, and this is lesson 6 of the SuckHunt series of my Z80 programming tutorials. In this series, we're going over the code of the little SuckHunt game that I created. It's basically a Duck Hunt or Operation Wolf style game. It's a rail shooter which has some stereoscopy. You can see it just here. If we just start the game up, you can see basically what we've got is a game that you can control the cursor here, and then you have to shoot the bats that come onto the screen. If we just move it onto the main window over here. So we can pick up the gun here and then we can shoot the bats. But the point is it's stereoscopic, and that means that there's two images, one in red and one in cyan. And if you've got a pair of 3D glasses, which I should have lurking around somewhere here, if you've got 3D glasses, then you can see the game in stereoscopic vision. And the way this works is we draw two copies of the sprites, and the distance between them affects the 3D effect. So that's a very strong 3D effect, but as they get closer, it's a very narrow 3D effect, and the Z factor, the stereoscopic depth, is affected by the position of the two sprites. So we're going to be looking at this today, and we're going to learn how the drawing routines work to get that effect. Now, the code we're looking at today is the multi-platform code. So this is the code that's common to all systems. So you're not going to see pixel or byte shifting routines for VRAM. This is just the calculation code. Those we will look at later on in other lessons. At the moment, it's just the multi-platform code. Now, as well as the sprites, we're also going to look at the sound, because this game, like all of my current games, uses Chibi Sound, which is a simple sound driver I created that takes a single byte and it converts it to one of 63 tones with high or low volume and noise enabled or disabled. So it uses a single byte to do that. And what I've done is I've extended that to allow for simple sequences of sound bytes so that we can create little sort of sound changes, like a sort of arpeggio, or a beeping effect that goes up and then down again, or a sequence of noise effects. And it's used by this game to do a variety of little sound effects for when you collect a power-up, when you get sucked by the vampire bats, things like that. The music is done by Orchestracker again, so it's just for simple sound effects on multiple systems. Now, I am working on a more enhanced version of Chibi Sound, which is basically going to be able to do music. So this is kind of the precursor to that. It's better than Chibi Sound, but it's not really good enough for anything other than simple beeps. But we're going to look at that as well. So I think that'd be quite fun. Anyway, let's go over to the code. Let's take a look. Right. So the first thing we're going to be looking at is this draw sprite from IY function, and this will draw a sprite that is being pointed to by the IY register. Each of our sprites has a bank of 16 bytes which defines its width, height, position, VRAM of the sprite data, and etc., things like that. So that's what we point IY to when we run this routine. And the first thing it's doing is it's checking bit 7 of the program. The program is the command sequence that runs this object's movements and things like that. So the top bit is defined as whether the object is alive or dead, and if it's dead it shouldn't be shown to the screen. So if that bit is not 0, we're just going to return. What we do next, if the sprite does need to be shown, apparently, then we get the details of the sprite, the position of the sprite and the height and the width of the sprite, and then we run our cropping routine, which we looked at last time, and this will check to see if the sprite is completely on the screen or partially off the screen, and if it's partially off the screen, work out how much actually needs to be drawn. When that returns, it will set the carry flag if the sprite is totally off the screen. So if the sprite's totally off the screen, once again we return, which is why I said before potentially needs to be shown, because it might be off the screen. What we do next is we've got a sprite we apparently need to show. So we use getScreenPos, which is a platform specific routine to calculate the VRAM address that this sprite needs to be transferred to, and then we run the platform specific routine show sprite L, which shows the left eye sprite. And if we just go to my other screen here, this will typically be the red eye graphic here. Now depending on your 3D glasses, it might be a different color, but typically it will be the red eye there. So that's what we do. What we do next is we've drawn the first eye, but we now need to draw the second eye. So we need to draw the cyan one next. So what we do is we do get sprite settings from IY again, getting the sprite settings the same as we did up here, and this is because of course that they will have all of the registers will have been changed by show sprite L, but we've now got the next set of details for the sprite. Now when we crop a sprite, our do crop routine actually changes part of the code because it uses self-modifying code to change the get next line address. So here we're resetting it back to the defaults so that everything will by default run normally without any kind of cropping. What we do next is we take the Z position and we take the current stereoscopic depth setting, that's how strong the 3D effect is, and we shift the Z position to the right at least once or twice, and then depending on the Z effect. And what we're doing is we're taking the Z position and we're converting it to a much smaller number, because what we do is we add it to the X position, and this affects the difference between the two eye positions, and this is what gives the 3D effect and makes it stick in or out, depending on whether the right eye is drawn to the right or the left of the left eye. If it's drawn to the right, it will stick in, and if it's drawn to the left, it will stick out of the screen. Now, once we've shifted that to the right, we then add it to the X position and save the new X position, and then we're going to redo the crop based on that new X position, and once again we return if the sprite is completely off the screen. So we do that twice. What we do next is we calculate the screen position again, and then we use the second sprite drawing routine, show sprite R, which again is another platform specific sprite drawing routine. The difference between them is that they do the bit shifting so that the colors are different depending on the left and right eye. That's why there's two versions. And then what we do last is we reset again the get line routine so that the next sprite is drawn without any cropping. Now, it should be noted that if 3D is disabled, this show sprite R routine will probably just be a return. It won't actually do anything if 3D is disabled. So that's how we draw a single sprite to the screen. But we do have an alternative version called draw n sprites from IY, and this is for drawing a sequence of sprites, and we specify the number with B, our B register, because we've got a DJ and Z here, and all we do is we repeatedly do draw sprite from IY, and after each one we add the sprite data size, which is usually 16, to IY, and then we just repeat until we've drawn all the sprites. So just a simple routine there to draw multiple sprites to the screen. Now, our sprite routines are used also for fonts. We've got some font routines that are almost the same as the standard ones. In my tutorials, I always use character 255 terminated strings here, but that's because that's what Chibi Akamas used to use. And so I've modified them here because the sprite routines on this system are 3D and the font is also 3D. So we've got an X and Y position, which we load in with X and Y here from H&L. But we also have the potential for a Z position, and we load that in from the accumulator into the Z value here. So what I typically do is I set the Z position at the start of a series of strings, and then I just leave the Z position alone and just change X and Y, because typically on like the game over screen I might want the font sticking out or sticking into the screen, but it's probably going to be the same for all the text, so I only set it once. We've got a locate and print string routine here, which will print the string HL to the XY position DE here, and so that's just again just a quicker way of locating and printing in one go. And we've got a new line routine here which just moves us down one line of the screen here. So they're almost the same as usual. They've just been extended with an extra Z axis factor in there because this game does have that quirk of the 3D. But I would strongly recommend, if you're writing your own games, one thing that I have sort of learned to my detriment on this one is while I'm using the sprite routines for the graphics of the characters, I couldn't use them for parts of the introduction because of memory limitations. I had to use ones that used some compressed data, and it made the game much longer to port. My Grime game and things like that would typically take just one day to port, whereas this one took a week. It took 2 weeks in some cases, so very slow to port this game to new systems. And for that reason, you know, if you're designing a game for multiple systems and you understandably have time constraints, I would suggest you try and funnel all your graphics routines through a single platform specific module, even if that means sacrificing functionality here and there, because otherwise you'll be bogged down in platform specific development, and as I say, it's not great. So that would be my recommendation. But anyway, so that's the graphics routines we're looking at today. The last thing we're going to be looking at is the sound routine, and we've got this new sound sequence, so we're going to have a look at that. So Chibi Sound, as you may or may not know, takes a single byte and it makes a sound based on that byte, and the format is fairly simple here. The top bit is a 0 if it's a tone or 1 if it's a noise. So for example, the bit 1 at the top here suggests this is a noise effect because it's a fire, it's a sound of a shot. The next one is the volume, and that's typically always 1 here because we want nice loud sounds, and the rest are the pitch. So we've got a variety of things here, and what I did for this game is I wanted to be able to play sequences of sounds and just have a driver that would handle that for me. So every time a tick occurred, the sound would be updated, and at the times I specified, the sound would change as required. And so what we've got here is a byte that's passed a chibi sound, and before that there is a time, and that's the amount of time that this is the byte chibi sound should have. And so after 8 ticks we will move to the next one, and after 8 ticks we'll move on to the next one, and then that 00 here means that we're at the end of the sequence. So sound fire just has one command which lasts 32 ticks, and then the sound stops. It varies depending on the requirements, but you can see this one's a nice fast sound, lots of changes. But yeah, as I say, a very simple way of giving a bit more detail to the sound effects and have the sounds change while the game's running, so that there was no the game action didn't stop while the tune played, but I had a nice simple multi-platform solution here. Now I am using Arcus Tracker for my music, and that is a problem because I don't have Arcus Tracker for almost all of the non-Z80 based systems, which is why I'm writing my own music tracker. I'm writing a new version of Chibi Sound which allows for an octave, a pre-configured matching tones and noise and sound and volume effects, and it allows multiple channels, and I'm writing a music tracker and a music file format so that I can do all of this kind of thing on every system in my tutorial series. And it's taking a lot of time, so it's not finished yet, but as I say, that this is woefully inadequate, but this is where things come from, and so this is all I could manage for this game. But as I say, it's a good improvement on the previous one. So we have two routines we're going to be looking at here. Now, play sound sequence is what we use to instruct the driver to play a new sound, and when we run this we pass HL with the pointer to the sound we want to play, and the accumulator with a priority. Now let's suppose the player is frantically hitting that fire button. We're making firing sounds, but then the player gets hurt or collects a power up, and that's far more important than hearing that fire sound. So the way we deal with this is we give each sound a priority, and if a sound is attempting to play that is less important than the sound that's currently playing, the low priority sound is ignored, and that's what we're doing here. We're comparing the priority of the current sound to the new one, and we're ignoring it if it's lower. If it's higher though, we are loading in the new time for the first sound, and we're updating the sound sequence accordingly. So we're updating the new address of the sound that's playing and setting the new sound timeout. So that will update the sound next time the update sound sequence is run, read in the new sound and play it. And so we're going to look at that now. So what we're doing here is we are checking the current sound timeout, and we are just seeing if that has reached 0 yet, and if it's not, then the current sound is still playing. But when it reaches 0, we actually want to read in the next sound in the sound sequence, and that's why when we wanted to force a sound to play, we set the sound timeout to 1. So we read in the address of the current sound sequence here, we read in the new sound timeout, that's the time that the next sound is going to play for. We read the byte for Chibi Sound. As I say, Chibi Sound just takes a single byte, and we send that to Chibi Sound, updating the address of the current playing sound sequence for next time. So that's what we do. Now, when the sound ends, we jump to sound silent, and we set the sound priority accordingly, and that will stop the sound. So there we go. So that's how we set the sounds with this simple driver. As I say, it's not great, but it added a little bit of enhancement to the simple Chibi Sound driver, and it allowed me to get some sound effects into this game very easily. And we'll be looking in the future, probably in a few months, when the new sound and music program is finished. And hopefully we'll be able to see something a bit more advanced that allows us to play proper music and do little sound effects and things as well on a wide variety of systems. It's already working on Z80, 6502 and 68000, and the way I'm writing it, it will be portable to any of the other systems in my tutorials, and hopefully I'll be able to port it to all of them. So we'll see that later on. Anyway, you can of course go to my website. You can download the source code to the SuckHunt game, and you can download the built game and have a go with it if you want to play a silly little game. As I always say, you're welcome to use the source code from SuckHunt in any way you want, because that's what it's there for. It's just a little practice game. It's not any amazing thing that has any commercial value, so go ahead and make any use of it you can and have some fun with it. Anyway, I hope you've enjoyed this. If you have, please like and subscribe. If you want, you can see up there, you can buy my book. My book is now available for sale on Amazon. It covers Z80, 6502, 8000, 8086 and ARM, and it's aimed for beginners, so hopefully you will be able to understand at least some of it. And as I say, if you want to support my channel and my programming, it's an easy way for you to get something, and it really helps me out, so consider doing that. Of course, please like and subscribe as well, all that kind of thing, which helps me out on YouTube. Hope you've enjoyed this. Thanks for watching today, and goodbye.